everybody, this video is going to be about the basic gas law equations that we'll be using in this chapter. There will be other more complicated equations that we get to towards the end of the chapter, but these are the main basic ones that we like to start off with. Before we get to the equations, there's a couple of odds and ends that we need to talk about in order to be able to use the equations. The first is that we're going to be using something called Kelvin. Kelvin is just another temperature unit. You're probably familiar with Fahrenheit and Celsius, but Kelvin is just a different one that we're going to be using. We will be using it for our gas law equations. The reason we're going to be wanting to use Kelvin is that we do not want to end up with any negative numbers. And so this will prevent us from getting nonsense answers. We're not going to be able to have things like negative volumes and negative number of moles and things like that. And so that's what's going to require us to use the Kelvin unit. To convert from Celsius to Kelvin, you just add 273. Sometimes people will ask, do we need to know how to convert from Fahrenheit? And my answer for that is no. I don't even remember how to go back and forth from Fahrenheit to Celsius ever, right? If I need to know that, I would just look that up on the internet. But from Celsius to Kelvin, you're going to add 273. Now, there are other decimals we can add if we wanted to be more specific, but 273 is plenty good enough for the class that we're in. The reason we want to use Kelvin is because we want our zero temperature to be an actual zero. So remember that temperature measures the molecular motion. And so if we want zero to mean the molecules are not moving, then it wouldn't make any sense to use a negative temperature, right? We're not going to have negative amount of motion. And so in order to make sure that we have answers that are all going to end up positive, we need to ensure that our temperature is always going to be a positive number. And so that's why we use the Kelvin and not Celsius or Fahrenheit. So we call 0 Kelvin absolute zero. And the reason that's such an important thing is because that's the point at which there's no molecular movement. We like to say zero really means zero. And there's a lot of really interesting research out there, people trying to reach absolute zero. We've never gotten to that point. If we did, people aren't really sure kind of what would happen, because a lot of the concepts that we have about how atoms work and all the quantum mechanics behind them come from the idea that you can't really know the position of something and its speed at the same time. And if you can make an atom stop moving down to the electron level, then you would know both of those things at the same time. You'd know where it is and you would know its speed. And so kind of all of our math would fall apart at that point. And so they've never gotten to absolute zero. They've gotten very, very, very close, but they haven't actually gotten there. There's a nice documentary called The Race for Absolute Zero. It goes over like the research and stuff. Some years we have time to show that. Otherwise, you could probably find it online somewhere if it's interesting to you. Another little odds and ends that we need to cover is the units of pressure that we're going to be using. There's lots and lots of options. Different problems will use different pressure units, and you just use dimensional analysis to convert. An atmosphere is one that we typically use a lot. It would be the pressure when you're at sea level, 1 atmosphere of pressure. That's the amount of, the pressure that's coming down on you if you were standing at sea level. PA is pascals. kPa is kilopascals. This is millimeters of mercury. This comes from a device that we use called a barometer, which is a tube that literally had mercury in it, and you would measure the height of the mercury column. And so the taller the column, the more pressure there was. We have one called torr. You might have heard of PSI, that's pounds per square inch. Sometimes like if you're filling up the tires on your car with air, we usually measure the pressure in the tires as PSIs. So you would just use dimensional analysis and use these as conversion factors. Another odds and ends is what we call STP, which is standard temperature and pressure. So sometimes we like to take shortcuts. If you remember on your mole highway, there was a shortcut called molar volume. And so that was a shortcut you could use where you were basically making a conversion factor out of a memorized answer to certain temperatures and pressures. So if you are at what we call STP, you're at 0 Celsius, which is the same as 273 Kelvin, and you're at 1 atmosphere of pressure, which is the same as 760 millimeters of mercury. So you have to meet both of these conditions. And the nice thing is this lets us not have to explain in quite so many words what our temperatures and pressures are sometimes. I can just tell you, you're at STP, or assume you're at STP. And it also allows you to use that molar volume conversion factor sometimes. Okay, so on to the basic gas law equations. You do need to memorize them. The nice thing is that there is some common sense and some real life experience that will help you remember the equations. And they're pretty similar, and so you'll kind of get used to some patterns, and then I can show you some tricks as we get to some of the more complicated ones where you could even derive the equations yourself if that's easier for you than memorizing. Doesn't really matter to me how you end up going about it, but you do need to be able to know them to do the problems. So the first is called Boyle's law. You're going to notice that they have a starting set of values and an ending set of values. The gas law chapter is a lot of problems about changes. If we're at one set of conditions when we start, and then we change something, what will we be at when we're done? So there's a lot of starting and ending values. We use 1s to represent the starting values, 2s to represent the ending values. Boyle's law is about pressure and volume. So when I change the pressure or volume, how do the other ones respond? So when we're doing Boyle's law calculations, we don't care about the temperature, and we don't care about how much gas we have. We don't care about the number of moles. Those are held constant, and so we're not going to worry about them. Most of the time, these problems are done in what we call closed containers or a closed system, so that we can't have molecules adding or escaping. So it's not going to change the number of moles. We say that Boyle's law is an indirect relationship. Sometimes in math class, instead of saying indirect, they use the term inverse. It means the same thing. It means when one goes up, the other goes down. And that kind of makes sense. If you have a container and you raise the pressure on it, the volume is going to shrink, right? You're squishing those atoms closer together. You're squishing those molecules of gas closer together. You can see it on a graph like this, right? As we increase the pressure going to the right, we see the volume goes down. It is important to be able to recognize on a graph which equation we're using. By looking at the axes, you can see, right, because we label them, and then the shape of the line on the graph will also help you with the conceptual part. Right? If one goes up, the other goes down. If one goes down, the other goes up. We can see that on our graph. All right, the next law is called Charles's law. Charles's law is about volume and temperature. And you should notice on this one, they're being divided. We keep the 1s on the same side and we keep the 2s on the same side. Right? Starting values, ending values. The biggest issue that we have with Charles's law is when you have to solve for something on the denominator. Your algebra needs to be strong enough to do that, okay? We have math prerequisites and suggestions for a reason, and the main reason is being able to isolate a variable. My personal preference is always to plug my numbers in and then solve for what's missing. Some people prefer to rearrange the equation first and then plug their numbers in. It doesn't matter to me. You're going to get the same answer either way. I will say, I see so many mistakes this chapter from people thinking that they're doing what math teaches them is called cross-multiplying. Okay, cross-multiplying is not a mathematical operation, right? It's a trick. They're teaching you a trick because, they're worried you can't actually isolate a variable step by step. So I caution you against that kind of a math trick because I see people trying to cross-multiply at times when it's not appropriate or they do it wrong. And so my suggestion to you is to always just rely on your basic math principles. If you're trying to solve for something on the bottom, multiply both sides by it to get it back onto the top, right? The opposite of division is multiplying. Opposite of multiplying, dividing, right? Rely just on basic math principles and not tricks. I see so many mistakes about it every year that I just want to caution you against this cross-multiplying trick. If you're really good at it, great. Just be careful. I see it go wrong very often. All right, moving on. Let's look at the graph. So, Charles's law is going to hold pressure and moles constant. We're not going to change the pressure. We're going to let the size of that container change, right? It'll keep the pressure the same. And then we should notice if your temperature goes up, your volume is going to go up. And that kind of makes sense if you think about what temperature means. It means the molecules are going to be moving faster. They're going to be hitting the sides of the container more often. And to make sure that the pressure stays the same, the container will need to get bigger to alleviate those extra collisions, right? To keep those from happening because we want to keep that pressure the same. And so temperature goes up, the volume goes up. One thing you should notice and be able to explain to me is that a Charles's law graph does not touch zero down here. We will never, ever, ever reach zero volume because the atoms themselves take up space. Now, they don't take up very much space, right? It's very, very tiny, but technically, we cannot get to zero volume. And then the other interesting piece is people don't even know if we could get to 0 Kelvin either, right? And so we're not going to be touching the 0 point on our graph. Next is Gay-Lussac's law. This is very similar to Charles's law, isn't it? But instead of volume over temperature, this is pressure over temperature. So this time, we're keeping volume and moles the same. If the temperature goes up, the pressure goes up. Because if its temperature goes up, the molecules are going to move faster. You're going to have more collisions with the container, and that's going to be an increase in pressure, right? Now you're going to notice too that it's not going to go all the way to the 0 point. The reason for that is a little different here. That's because at some point, if you increase the if you get cold enough, right? Say we're at 2 atmospheres of pressure, right? And we're at, this temperature. Instead of being a gas, it's going to be a liquid, or maybe it'll be a solid, right? And so at some point, we kind of add a dotted line here because it's not really a gas law anymore, is it? If it's on a gas phase. So because of that temperature portion there, we do end up tending to draw a dotted line here. Next is Avogadro's law. You should recognize that name, right? So we're going to have volume here, and I'd be willing to bet you could guess what N would be. If this is Avogadro's law, he talked a lot about how many particles were inside a mole. So N will be the mole. Now, it does feel really silly to have mole be represented by an N, but it is what it is, okay? So this looks very similar to the others, right? It's another direct relationship. This time pressure and temperature are held constant. If moles go up, your volume has to go up. If you add more particles, you need more space, right? If you don't want your pressure to change, you don't want your temperature to change, you're going to have to make the container bigger. Now you should notice here that this graph does go to the 0 point, does it? Because if you have 0 moles of gas, that will take up 0 volume. So that's something that is a little bit different here, is that 0 makes sense for Avogadro's law. Now, you can combine all of these laws together. So if we wanted to have pressure, volume, and temperature together, we'll worry about moles on another day. Okay, let's not worry about moles today. Let's just do pressure, volume, and temperature. We can squish them together to make what's called the combined gas law. So for the combined gas law, we're going to just hold moles constant. It combines all the common units that we use. It's not that we can't change the number of moles, but we don't often do it. It's normally just pressure, volume, temperature that we're concerned about. So this is a very common law, combined law. Now, one thing that's kind of neat is if you start with the combined gas law, you can actually figure out the other laws by just crossing out which variables are not changing in your practice problem. So for example, we start with the combined law, and let's just say temperature doesn't change this time. What does that turn into? It's not the combined law anymore, now it's Boyle's law. Well, what if this time pressure doesn't change? Pressure stays the same. We don't care about pressure, we don't mention it, it's not changed, it's held constant. Get rid of it. Well, it's not the combined law anymore. If it's volume and temperature, it's Charles's law. What about if this time volume doesn't change? The container is going to stay the same size. Well, pressure over temperature, that's not combined gas law, that's Gay-Lussac's law. So hopefully you can see that this combined gas law can be handy. If you forget any of the others, just jot the combined gas law down and then cross out what you don't need. So it's a pretty handy way if you have a moment where your brain freezes and you can't remember anything, right? You can use that combined law to help you figure out the other laws. So one of the things I also just want to really encourage you to do is always stop and ask yourself if your answer makes sense for this chapter, right? Think about okay, well, if I increase pressure, it should get smaller. My volume should be smaller when I'm done, and see if it works, right? So often we can catch our algebra mistakes if we stop and think about whether or not conceptually this matches our common sense experience. Gas laws are one of the few times this year where we have a lot of real life experiences. Like if you ever take, a bag of chips right up to the mountains, right? What happens to the size of the bag? Or if you take, a water bottle on an airplane, right? Those kinds of common sense experiences. If you leave a container of soda in a hot car and it heats up too hot, what's going to happen, right? So you can use that common sense real life experience to help you with these problems. So one of the things that can be good in the beginning is before you even start the algebra, just jot down a little up arrow or a little down arrow so that you can remind yourself, my answer should be bigger, my answer should be smaller. And also thinking about what the particles themselves are doing will help you with the conceptual aspects of the chapter. Remember that the particles are moving. When they hit the container, they exert pressure, right? If the temperature goes up, they move faster. They're going to hit things more often. You're going to have more collisions. You're going to have more pressure, right? So you can think about the particles and their motion to help you with the conceptual pieces. We have a huge problem this chapter with people relying on their math skills. They're very good at math. They're very comfortable with math. They ride through the practice problems, because they're mostly algebra based, right? Just a lot of math to practice. And then you get a quiz and there's a conceptual question and people miss it. The problem for me as a teacher is that I have to give you lots of the math problems to practice because math takes, repeat exposure. It takes repetition. You have to practice the math over and over. There's not a lot of conceptual questions I can ask you. And so you may not get as many practice problems on the concepts as you do on the math. That doesn't mean they're less important. It means that when you do get a conceptual question, you better be paying attention to it and you better understand it because it has a high likelihood of being something you may see on a quiz or test. So I'd just like to caution those of you that feel really good about your math skills that this chapter can be more challenging than you think it is. Because if you just brush off all those concepts, that's not going to work for you long term. Okay? All right, everybody, that is the end of this lecture. I hope that was helpful. Bye.